Good afternoon, everybody. Sorry I cannot join you in person due to a family medical emergency. I'm grateful the session chair Jake and Rachel gave me the opportunity to share this new method, dense multiple, that is using neutron contrast variation data for structure density reconstruction. In neutron scattering, one big advantage, as we know it, is contrast variation. The contrast variation is especially powerful to study a complex made of different components. For example, here we can say scattering density for different types of molecules are distinct. For example, lipid and proteins can be contrast matched at different ratios of D2O. So we can study their structure separately in a complex with contrast variation. Traditionally, beads modeling is used for ab initio reconstruction in solution scattering. For example, moons are packaged from Svergen's group, but there are a number of inputs required, such as subphase volume, sometimes are difficult to estimate accurately. Also, using beads means either 1 or 0 at certain part of the structure, which is not true for most structure as their internal density varies. Recently, with development of DENSS, an iterative structure factor retrieval ab initio method, a density reconstruction becomes possible for either SACS or single sense data. So basically, it starts with a random model's density. During each iteration, structure factors with both amplitude and phase were scaled to the experimental isotropic averaged 1D scattering data. Once the model scattering intensity is convergent with the experimental data, we can consider the phase carried by model structure factors are able to represent the actual phase. Of course, the density distribution inside the structure is still limited by the resolution limit of small angle scattering data, so it can only resolve relatively large scale features. High frequency information, which gives high resolution structure, is filtered. But of course, if the higher Q data, for example, wide angle scattering data can be included, the resolution could be improved. So here is a workflow for dense multiple using contrast variation data. For the input, in addition to the experimental scattering curve at different contrast, the background buffer scattering density are also part of the input, which can be approximated from the D2O ratios. Then it started with a common starting model density. With the starting model density, it's used different background scattering density to generate different initial densities for different contrast. Then the different densities were converted to structure factors by fast Fourier transform, FFT, and then to the scattering intensities that can be scaled to the experimental density. During this process, the scaling for each contrast is performed individually. After the scaling, a series of new densities are generated by inverse FFT, and then add back the subtracted background scattering density within the support region. And then those densities can be combined after the iteration. And after the iteration, how and when to combine the densities needs some further consideration. So the most obvious option was a simple mathematical average across all contrast in the 3D real space arrays for those densities. And also an important factor to consider is when to average during the iterations. We determined that averaging the densities of each contrast should occur after the real space constraint. Another question is how often to perform those averaging operations. What we found is the orientation and location of the densities from one contrast will drift significantly in real space. and it's very expensive to align them among all the contrasts. So we decided to average at every iteration to essentially enforce their alignment. And at the end, if the average chi-square value is no change from the previous averaged, for example, 100 chi-squared, then the break condition is reached. So there is no improvement in the iterations, and we determine the algorithm has converged. That is where the iterative process stops. So the first test we did is a single phase test, just one phase structure, measured at different contrast. The simulated data are from models with scattering density of equivalent 42% D2O. Those are true structures. The dense multiple construction were done using background buffer in 0%, 80%, and 100% D2O data. So as you can see, the results are as good as damming reconstruction results. And you can see the cylinder disk model is challenged for all the programs in both dense multiple and damming. So here are some details from a sphere and hollow sphere results compared to dense, the single dense. You can see the dense multiple results, it looks more rounder and more uniform than single dense. And for the hollow sphere, the result is more enclosed than single dense without the artifact of broken enclosure. And given the resolution limit of SANS, I think somewhat sharp angles in the structure are acceptable. To test dense multiple for multiple phase complex, we use a few different models. Here are showing their structures and the scattering density at different part of the structure. And they are reconstructed in the simulated data of 0%, 65%, and 100% D2O background buffer. In the two-layer onion, a lalodisk-like cylinder, and the two-layer long cylinder model, the overall structure resembles model very well, and the internal density show different phases too. However, the three-layer onion model is not quite successful in this case. This example brings up an important point of phase of contrast inclusion in use DENSS. So here we demonstrate that the use of different contrasts need to be considered carefully, especially for those contrasts that match out a component completely. For example, in the simulated data for this three-layer onion model with 42%, 65%, and 100% contrast, it was measured in a background with 0%, 65%, and 100% D2O, coinciding with a significant numbers of phases in the model. So we believe that aligning and combining the subphase among different contrasts during the iterations becomes very challenging because the parts of the structures are never shown up in those contrasts in the searching space. So we have found that with dense multiple, there is no need to use fully contrast matched data for a component. You can use a contrast in between those components. Scattering density is more effective. So now let's talk about the absolute density. So here we are using absolute scaled data and also the background scattering density as input. In principle, dense multiple can provide a structural result with absolute density in the iterative process. However, while we found the different phases can be differentiated very well, but the final density value is not in absolute density as expected. For example, in this structure with three phases, the final results for the three phases can be well differentiated. And if you look at the density histogram, the density value is not in absolute scale. They can be differentiated very well for those different numbers, but they are not in absolute value. So we figured out that the scaling process for the structure factor from different contrast is likely to mess up the density values to be realistic absolute density. And of course, if you look at the histogram, we can differentiate the phase well, and we can scale them manually very well. Here are some examples from lipid nanodisk reconstruction from dense multiple. As we know, the disk has been a challenge shape for many programs such as single dense and damming or damming package. As you can see, the disk shape is well constructed by dense multiple use contrast variation data. The first nanodisk is deuterated membrane scaffold protein with deuterated DMPC. The contrast matching point of lipid is about 100% D2O, and the contrast matching point of the membrane scaffold protein is about 80% D2O. As you can see, the results reproduce the density distribution fairly well. The center part of the structure has slightly higher density than the outer part. And the second nanodisk is a mixture of the deuterated lipids and the prochiated lipids with prochiated membrane scaffold protein at a contrast match point of 42%. As you can see, the distribution of the lipids inside this nanodisk is not uniform. We think that is due to the inhomogeneity inside this nanodisk might be due to the distribution of the DMPG. So with this test, we believe dense multiple is very effective for neutron contrast variation data. And we already put the code in public domain, so you can download the code to test on your contrast variation data, or you can further develop these methods based on the code we have. And the manuscript is currently under review, and we already put the manuscript in the preprint server, so you can take a look at the details of this method. So with that, I would like to acknowledge my intern student, Jake Sumter, working on this project. Did a lot of development and coding and testing, and also involved a lot of works during the COVID-19 in the past 2 years. And we thank Chu and Swati and Hugh to provide the lipid nanodisk for science experiments. And this project is supported by Center for Structural Molecular Biology program in Oak Ridge, which is the operator of bioscience instrument. And also my job is supported by Second Target Station project of ACNS under DOEBS. And thank you for your attention. And I hope you can contact me for any further questions. I would love to help you to test those programs. Thank you.